Welcome friends, Igor is here, and in this video we will work with linearly dependent and linearly independent sets of vectors in arbitrary vector spaces. In this lesson we will extend the notions of linear dependence and linear independence from column vectors to arbitrary vector spaces, and we will learn how to check if a given set of vectors is linearly dependent or linearly independent in a given vector space. Let's get started. We can construct linear combinations in any vector space, and every vector space has the zero vector. Therefore, the notion of relation of linear dependence makes sense in the context of an arbitrary vector space. In particular, we have the notion of a trivial relation of linear dependence. Now, similarly to the column vectors, we say that a set of vectors in a vector space is linearly dependent if there is a non-trivial relation of linear dependence on this set, and the set of vectors is linearly independent if the only relation of linear dependence is the trivial one. Let's look at an example. The vector space is 2 by 2 matrices, and we are given a set of 3 vectors in this space. We need to determine if this set is linearly independent or linearly dependent. To answer this question, we construct a relation of linear dependence on this set. Let's understand what this equation says. In the vector space of 2 by 2 matrices, the zero vector is the zero matrix. Also, we can use the explicit definitions of operations in this vector space to compute the linear combination. First, we scale each matrix by the corresponding scalar, and then we add the matrices. We can do this because we know what the operations are in this particular vector space. This results in the equality of two vectors in the vector space of 2 by 2 matrices, but this equality is equivalent to 4 separate equations. These are equations in unknown scalars, and these equations form a homogeneous linear system. To solve this linear system, we find the reduced row echelon form of the augmented matrix, and we see that this linear system has only the trivial solution. In turn, this implies that the only relation of linear dependence on the set S is the trivial relation, and we conclude that this set is linearly independent. Note the similar nature of this computation to the column vectors. In the column vectors context, the question of linear dependence or linear independence always reduced to solving homogeneous linear systems. In this vector space, we also obtained a homogeneous linear system, and we were looking at the solution set of the homogeneous linear system. If matrices was too easy an example for you, let's consider the crazy vector space, which we defined in one of the previous videos. The elements of the crazy vector space are ordered pairs of numbers, and we take a set of 2 elements of this space. To determine if this set is linearly independent, we construct a relation of linear dependence on this set. Then we use what we know about this vector space to simplify this equation. First of all, we know that the zero vector in this space is the pair -1, -1. That's one reason why it's called the crazy vector space. This must be equal to this linear combination, and we use the definitions of the operations in the crazy vector space to compute this linear combination. First, we do scalar multiplication, and to scalar multiply a pair, we multiply each component by the scalar, we add the scalar, and then we subtract 1. We clean up the expressions, and the next step is to add 2 vectors. To add 2 vectors in the crazy vector space, we add the corresponding components, and then we add 1 to each component. Once again, we simplify the expression. The relation of linear dependence that we started with results in this vector equality in the crazy vector space. But this vector equality is an equality of 2 ordered pairs. They are equal as long as they have identical components. This gives us two linear equations in the unknowns alpha1 and alpha2. And even though the zero vector in this crazy vector space is the pair -1, -1, notice how the resulting linear system is still somehow homogeneous. You can easily check that the coefficient matrix of this homogeneous system is non-singular, and therefore this system has a unique solution. This unique solution must be the trivial solution, and therefore the only relation of linear dependence on the original set R is the trivial one. This proves that the set R is linearly independent in the crazy vector space. But what I want you to really notice in this example is that even though the zero vector in the crazy vector space has nothing to do with zero numbers when we set up the linear system, it was still the homogeneous linear system. If you found this video useful, then please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will define the notion of a spanning set of a vector space. I will see you later.